So I'm going to break continuity entirely and tell you that I filmed this video days and days ago, probably actually weeks ago. So this is another cool 1 minus gamma thingy-majig, but it involves a very, very weird integral of something that's not entirely continuous, and because I'm weird, I've decided to walk around while doing this intro. Here you go. The heck? So to start off, we need to consider a rather weird integral that may seem a bit odd at first, but it's totally relevant. We need to consider the integral from 1 to n of the floor of x divided by x squared dx. Now, what is the floor of x? Well, the floor of x is a very simple concept. It's simply the nearest integer that is less than or equal to x. So if x is already an integer, then the floor of x is just x. But if x is not an integer, you're essentially just taking away the fractional portion of the number, right? You're just removing it from the number. So you're essentially rounding it down no matter what the decimal part of x is, right? It's not the nearest integer, it's the greatest integer function. So the integer that is just below x if it isn't already an integer. And so what we need to realize is that because of that, the floor of x is always a whole number, right? And that means we can sort of write it in an odd way, a very strange way. We can write it like this. So we can write it as the integral from 1 to n, and I'm just going to factor the 1 over x squared out here. And we're going to write the floor of x as a sum of all the numbers k that are greater than or equal to 1 and less than or equal to x. And we're going to sum that over 1. So essentially what I'm saying with this is we're going to add as many 1s as there are k's between 1 and x. So think about that. If x is pi, then that means the number of integers from 1 to x are 1, 2, and 3. So if x is pi, then the floor of x is 3, right? And so we're going to add 1, 2, 3, right? It's all k's that are greater than or equal to, all integers k that are greater than or equal to 1 and less than or equal to x, right? And so we're just going to add 1 that many times. That's the same as the floor of x because the floor of x is always an integer. So I hope that's clear. If that doesn't make sense immediately, try to ponder that. I'm just adding as many 1s as there are integers k greater than or equal to 1 and less than or equal to x. Okay? And that's a good definition of the floor function. And then what I'm going to do is I'm going to simply break this integral up into a sum of multiple integrals. So we're going to have the integral from 1 to 2 of 1 over x squared plus the sum over k's that are between 1 and x of 1 dx plus the integral from 2 to 3 of those things, right? So 1 over x squared times the sum from 1 less than or equal to k less than or equal to x of 1 dx plus dot 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 all the way up to the n minus 1 to n. So 1 over x squared times the sum from 1 less than or equal to k less than or equal to x of 1 dx. So I hope that's clear what I'm doing. I'm just adding up 1 to 2, then 2 to 3, then all the way up to n minus 1 to n, which is going to all combine together to give you this integral right here. I hope that's clear, right? And again, just to reiterate, this sum is over as many 1s as there are k's that are integers between 1 and x. So that will always give the floor of x. Again, just try to ponder that, try to think on that, see if that makes sense to you. And what we have to do now is realize that because these are integrals of x, and we're doing essentially the floor of x depending on the values that x takes on, right? Essentially because we need this to add up to n, right, the integral from 1 to n, we can treat these as sort of these integrals going from 1, including that point, up to all numbers less than 2, right? And not including 2 in this integral is not going to take away any of the area under this function because the 2 is here. And then we go to every number up to but not including 3. And then we start at 3 in the next one and go to every number up to but not including 4. All the way up to here where we start at n minus 1 and go up to every number but not including n, right? So we're sort of saying that this integral is for x's that are less than or equal to 1, I'm sorry, greater than or equal to 1 but less than 2. And this one is for x's that are greater than or equal to 2 but less than 3. And this one is saying that this is for x's that are greater than or equal to n minus 1 but less than n, right? So the total integral goes from 1 to n without copying any numbers, right? 2 is not included in this integral, but 2 is included at the lower bound of this integral. So I hope you understand what I'm saying. I hope that makes sense. That way, what we can say now, because x stops at 1 here, we can say that the floor function evaluates to 1 in this instance. So we actually end up with the integral from 1 to 2 of 1 over x squared times 1 dx. And here, because x goes up to 2, right, starts at 2, we can, but doesn't get all the way up to 3, we can say that this is the integral from 2 to 3 of 1 over x squared times 1 plus 1, which is just 2. Right? Because the biggest integer that x gets to in this interval is 2, right? We're saying that it's strictly less than 3 over this interval. It doesn't get to 3 until the next integral from 3 to 4. I hope that makes sense. And this is dx, and then we're adding dot dot dot, and then the last one is going to be the integral from n minus 1 to n of 1 over x squared times n minus 1 dx. I hope that's clear what I just did there, right? Because x is the biggest integer that we're seeing in each interval is the lower index, right? The lower index of the, or the lower bound of the integral. Then that floor function is going to add up to that integer, right? The bottom is 2, the floor function adds up to 2. The bottom is n minus 1, this floor function adds up to n minus 1. I hope that's clear. What that means, interestingly enough, is that because these are all constants, we can factor them out. So we end up with 1 times the integral from 1 to 2 of 1 over x squared dx plus 2 times the integral from 2 to 3 of 1 over x squared dx plus dot 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 all the way up to n minus 1 times the integral from n minus 1 to n of 1 over x squared dx, right? I hope that's clear. I'm just factoring out that constant that we got from the floor function to the outside of each integral. What we can do is actually rewrite this now. We can rewrite this as, if we consider what's going on here, that means we have like 1 of these, 2 of these, 3 from 3 to 4, 4 from 4 to 5, and then n minus 1 of the integrals from n minus 1 to n, right? So what we can actually do is take this one of these, 1 of the third one, 1 of the fourth one, 1 of the n minus first one, and combine them all together into one integral from 1 to n of 1 over x squared dx. Okay? I'm just taking this, and then 1 of these, and then 1 of the next one, all the way up to 1 of these, and combining them into an integral from 1 to n. But then notice, I've taken the only one of the integrals from 1 to 2 that I had, so that's gone now. Now I have 1 of these left, I have 2 of the ones from 3 to 4 left, I have 3 of the ones from 4 to 5 left, and I have n minus 2 of the ones from n minus 1 to n left. I know this is really wordy and symbol heavy, but it's all following, which means because I don't have any of the ones from 1 to 2 left, I can take one of each of the ones that I have left and do an integral over 1 over x squared from 2 to n, right? So I can do that. I hope that's clear. Now that I'm out of both of those, I now have the ones from 3 to 4, and then 4 to 5, and then 5 to 6, all the way up to n minus 1 to n. But because I only have one of those ones from 3 to 4 left, I can take it and all the others, one from each of the others, and then make an integral from 3 to n of 1 over x squared dx. Which means I can go all the way up to my final integral of, because I'm going to end up with one of these left after all of those, and the last one of those is going to make the final integral from n minus 1 to n of 1 over x squared dx. I hope that's clear what's going on here. I'm literally just, because I have different amounts of each of these unit integrals, I'm taking one from each at a time and building new integrals out of them. I hope that's clear what I'm doing. And the cool thing about that is now I can make a series out of all of these, right? Because I can add from 1 to n minus 1, all of these together. I can add from 1 to n minus 1, all of these integrals together. So I'm going to erase the intermediate steps, and I'm going to write what's equal to this up here. So because I have now a series of integrals from 1 to n, and then 2 to n, and then 3 to n, I can use the lower index of these integrals as an index for my sum, right? So I can say the sum from k equals 1 to n minus 1. Before I do that, notice that I can technically say that I have an extra integral here that goes from n to n, right? If I do that, if I have that here, n to n, right? That, of course, is equal to 0, right? Because I'm going from n to n, so it has no area underneath it. But because I'm adding 0, I'm not actually changing the value of the total sum, so I'm actually going to add that on as well. So my sum can actually run from 1 to n instead of 1 to n minus 1. So I'm not adding anything, right? It is equal to 0, which means it's a valid thing that I can just tack on because it's not adding anything at all. So I hope that's clear. Now I can have this index run from 1 all the way to n, right? Without any trouble. So this thing that I've just derived so far is going to be equal to the sum from k equals 1 to n of the integrals from k to n of 1 over x squared dx. So I've just shown so far that the integral from 1 to n of the floor of x divided by x squared dx is equal to the sum from k equals 1 to n of the integrals from k to n of 1 over x squared dx. And I know that was a big mouthful of math, but I promise it's all going to work out. So if it wasn't exactly clear what I was doing in this video, go back, watch it again, try to follow every step that I'm doing because they all are relevant. The best part about this, though, is we know what the antiderivative of 1 over x squared is. It's negative 1 over x, which means we can rewrite this as the sum from k equals 1 to n of negative 1 over x evaluated at n and k. Right? Using the negative to flip the bounds, I can just say it's the 1 over x evaluated from at k and n instead, and we can rewrite this series as the sum from k equals 1 to n of 1 over k minus 1 over n. Right? But wait a second. What's the sum? Wait, this looks kind of familiar, doesn't it? This isn't going to infinity, so I can break it up into two different sums, and I get the sum from k equals 1 to n of 1 over k minus the sum from k equals 1 to n of 1 over n. Well, 1 over n doesn't depend on k, so this one I'm just adding 1 over n times, which means this is n times 1 over n, and look at that. That's the nth harmonic number right there. So this is equal to the nth harmonic number minus 1 over n times n. But what's 1 over n times n? It's 1. So this is to say that the integral from 1 to n of the floor of x over x squared dx is equal to the nth harmonic number plus 1. So hey, there's another actual representation of the nth harmonic number, right? There it is, right? The nth harmonic number is 1 plus the integral from 1 to n of the floor of x over x squared dx. But this wasn't a video about finding another representation of the harmonic numbers, though this is perfectly valid. This is a video on figuring out something that's equal to 1 minus gamma. So that's what we're going to do now. Because how can we write the floor of x as something different? What did I say? It's x, but with the decimal portion taken away, which means we can actually write it like this. So this is equal to the integral from 1 to n, and this is over x squared, remember, dx. But the floor of x is x with the decimal portion taken away, and we have a symbol for that. It's x in curly brackets, right? So the floor of x is the same as the number x minus what's called the fractional part, which is usually denoted x in curly brackets. And so what I'm saying is, say we had x equals pi, right, which is about 3.14, then the fractional part of x is just pi minus its integer part, which is 3. So it's about 0.14159, whatever. So it's just the bit that's not the integer, right? It's the stuff after the decimal portion. If you ever see x in curly brackets like that, and you're not talking about, say, set theory, and you're talking about numerical amounts, it's always the fractional part at the end. So x minus the fractional part of x is sort of by definition the floor of x. So what we can do is now break this up into two different integrals. We have the integral from 1 to n. What's x over x squared? It's, 1 over x. So we have 1 over x dx. And now we have minus the integral from 1 to n of the fractional part of x divided by x squared dx. But what's this? We just did this in the last video, right? We know what the integral from 1 to n of 1 over x is. This is the natural logarithm of n. But because we know that this is equal to the harmonic numbers, the nth harmonic number minus 1, we can add this one over to this side and subtract the natural logarithm over to the other side. So we get the result that the harmonic numbers, the nth harmonic number, minus the natural logarithm of n is equal to 1, right? We're adding the 1 over to here and subtracting the natural log over there. We get 1 minus the integral from 1 to n of the fractional part of x divided by x squared dx. But now, all we have to do is take the limit as n goes to infinity of both sides. Well, what's the limit as n goes to infinity here? That's just going to turn this upper bound into infinity. But what's this limit? This is, of course, the Euler-Mascheroni constant, right? By definition. Which means if we simply just subtract gamma to this side and add this integral to the other side, we have the astounding result, my friends, that the integral from 1 to infinity of the fractional part of x divided by x squared dx is equal to also 1 minus the Euler-Mascheroni constant. Absolutely beautiful. Now, I know that this was a much more cumbersome argument than the other one, but I really, really encourage people to go back and watch the video and find every step that they didn't understand and really, really dig into it so that they grasp what's going on here. This very erratic function, right? This is the fractional part of x. Every x simply with the integer part taken away, divided by x squared, and the area under that weird curve from 1 to infinity, this very, very discontinuous curve from 1 to infinity, is exactly 1 minus the Euler-Mascheroni constant. Absolutely astounding result. And beautiful, beautiful result at that. And we actually got another representation for the harmonic numbers out of it, right? We discovered that the harmonic numbers are equal to 1 plus the integral from 1 to n of the floor of x divided by x squared dx. So we didn't just get this result out of it. We can erase the other stuff, but we actually even managed to walk away with another representation for the harmonic numbers, right? We now also have this under our belt. The harmonic numbers, the nth harmonic number, is equal to 1 plus the integral from 1 to n of the floor of x over x squared dx, right? Beautiful, beautiful result. So we have two amazing things from this video. So I hope that was enjoyable for you all. I know this one probably ran a little bit longer than the others, but it's a lot of cool math and a fantastic number, which is, remember, digamma of 2, right? The derivative of the gamma function at 2. So it's a beautiful concept, a beautiful quantity, I mean. And so I hope you enjoyed watching. In the next video, we're going to explore the reflection formulas for the digamma and harmonic functions. So thank you for watching, and I await your fantastic, probably amazing response to my previous video, Papa, because you always do great stuff, and I'm absolutely overjoyed to be your adversary. So, bye-bye. Quick little thing, this channel has an Instagram, so it is at whatthehectagon, of course, and it has a Twitter, and it is, of course, naturally, also at whatthehectagon. And my email is the incorrectly spelled whatthehectagon. Why spell check before you make the email, right? That you can't then change, at gmail.com. Now, all of these are in the description if you don't want to have to somehow watch the video and pause it and actually write it down. That's the stuff. Thank you for watching, and bye-bye.